Welcome. We're so glad you're here with us for today's Harper Lecture. The Harper Lecture series began in 1979 with Hannah Holborn Gray speaking in San Francisco. As the need for critical thought remains apparent in all areas of life, we proudly continue this signature program to bring you stimulating conversations and fresh ideas. Our UChicago community is a global one, and we are thrilled that technology can help us stay connected to one another. As you enjoy today's lecture, please note the following items. Your camera and video will be off. However, we encourage you to ask questions. Please use the Q&A box at the bottom of your screen to ask a question at any time during the talk. Closed captions are available by clicking the box at the bottom of your screen. Click Show Subtitles to enable this feature. If you're having trouble with audio or video, please try shutting down programs in the background, or you can dial in from your phone. Thank you once more for joining us. We couldn't do this without you.
Good evening. I am Lauren Henry, Executive Director of UChicago Alumni and a proud alum of the college. I'm thrilled to welcome you to tonight's Harper Lecture, Urban Crime Prediction, the Data, Ethics, and Biases of Predicting Events, with Professor Ishanu Chattopadhyay. Harper Lectures provide the alumni community with the opportunity to return to the classroom from wherever they are in the world, continuing our tradition of asking hard questions, dialoguing about critical topics, and pursuing new depths of knowledge and understanding. Thank you for joining us this evening for a discussion of the power and challenges of AI in law enforcement. We will look forward to opening the floor to your questions later in the program and ask that you share your questions via the Q&A box at any time. With that, it is my pleasure to introduce Professor Chattopadhyay. He is an assistant professor in the Biological Sciences Division and the Committee on Genetics, Genomics, and Systems Biology. His research focuses on artificial intelligence, machine learning, and the computational aspects of data science. His current work focuses on analyzing massive clinical databases to distill patterns indicative of previously unknown etiologies of complex diseases and understanding rare event dynamics in natural and human systems. He is the recipient of the prestigious Young Faculty Award from the Defense Advanced Research Projects Agency for his work on formal methods to study cognitive dissonance and opinion dynamics. Professor Chattopadhyay, thank you so much for being here with us this evening. I'll now turn the virtual stage over to you.
Thank you, Lauren. Welcome, everyone. We are going to talk about urban crime prediction and talk a little bit about AI, what its capabilities are, where it's going, and whether we should be concerned or happy. So 2023 is definitely going to be, or if not, it already is, the age of the AI, or the year of the AI. And unless you have been living under a rock, you probably have encountered or heard discussions about ChatGPT, which is a language model that can do some pretty amazing things. For example, to make this talk, I asked ChatGPT to write me a sonnet about AI. And I'm not a poet, but it seems to be pretty good poetry. It learns, it grows, it thinks, it reasons to, its power vast, limits not yet found. Sounds pretty profound and pretty poetic. So that's pretty amazing to think that what ChatGPT is under the hood is simply a model that generates text. Given a fragment of text, it is supposed to be able to complete it. That's all it does. But then it went and read everything that we have ever written down, everything, and in all languages. And once you put those two things together with the current computing power that we have at our fingertips, you get something like this, where it can write poetry, it can answer questions, it can do all sorts of pretty amazing stuff. So immediately, the question that everyone was concerned with, or everyone showed up and every kind of popped up in everyone's mind, is how should we constrain AI? How should we kind of hobble it? And that is kind of a reminiscent of what we had when Copernicus told us centuries back that the Earth might not be at the center of the universe, right? Like, crap, we are not special. And it's kind of a very similar crisis, right? Except it's not about cosmology, it's more about like the human intellect. So some of those concerns might be important to ponder on. And one question is whether it would be better in applications where AI is interacting, particularly in domains that are of interest to us, to have a human supervisor, like a human in the loop, if you may. That might prevent it from making silly decisions or be biased, be unfair to some of us. And that might not be an immediate solution. That might not be the obvious solution, so to speak, because, well, we see a lot of biases around us, and that is all produced by humans. So having a human in the loop might or might not make things better. So let's talk about crime. That's that's kind of the topic of today's talk, today's discussion, and whether it's a good idea to have AI tell us about future crimes. Does it allow us to kind of bring down crime rates? Is it a good thing in general? Does it make situations about existing biases or unfair treatments from law enforcement? Does it make it better, worse? Where it is kind of like, where do we stand on that? So it's crime and a problem that we should be worrying about, and whether we might need help from more advanced technologies to bring that down. It seems to be, it is an important problem. If you look at over the entire world, the leading causes of death, the 7th or 8th from the top is homicide, and that is in 2019, I think. So that's kind of an important thing to think about. However, before we go into what you can do or not do with AI in this context, if you were able to kind of predict crime that has not yet happened, the immediate question is, where does that leave us with free will? And this was a question that was asked of me to explain, to kind of opine on this in a podcast. And that's an interesting thing to think about, particularly if a machine can predict what crime is going to happen in future. It might imply that the perpetrator or the person committing the crime did not really have a choice. So how can you make hold them responsible for something that they didn't really have a choice in? It's an interesting question, and interesting conundrum. We'll come back to that later. Now, how difficult is it to predict crime? It depends on what you mean by prediction. If you're talking about predicting rates, like very broad predictions, then it's not that hard. In fact, sociologists have been thinking about how to predict or how to learn crime rates for a century or more now. In fact, if you plot the number of homicides for 100,000 Americans from 1900 to 2006, that's about 106 years, you see this very nice sinusoidal pattern, that periodic pattern that shows up. Now, don't ask me where this pattern comes from. I have no idea, but it is there. You can just look at the logs and plot it, and it's there. There's no AI algorithm needed to come up with this description. So this broad pattern seems to be very predictable, but that's not what we're talking about here. We're talking about predicting individual events. Can we predict a week from now there will be a car theft at the intersection of the 86th and Southwestern Avenue? So that's kind of what we're talking about, and how what would be our uncertainty in there. Can we act on that? Should we act on that? And stuff like that. So even with that, even at when we're talking about predicting crime or trying to predict crime at the level of individual events, that's not really a new idea. In fact, going back to Pred poll, that was one of the early attempts at it by Jeff Brantingham from UCLA. And the approach taken there in some of those early works was to identify hotspots, right? So the idea was that there are these problematic areas in cities, whatever area or region you were interested in, where the crime rates are high in those areas, and crime kind of diffuses out, if you may, from those hotspots. And that's not really a very good model of crime, right? I mean, crime is not like ink in water that it kind of diffuses out. And pretty much we can immediately think of counterexamples. For example, if your house gets broken into this Sunday, what are the odds it will be broken into again on Monday? Probably lower, right? If there's a homicide in some place, some area, what are the odds that there will be more homicides because of the homicide that already happened? In most cases, the odds will be lower because particularly in US cities, there will be a law enforcement response, and that would probably reduce the odds of a particular crime. Or if a particular group of individuals are going around robbing banks, for example, then the very fact that they cannot be at two places at the same time means that if they're robbing a bank here, they're not robbing the bank next to it. So it's not that things diffuse like that. The relationships that emerge has to be more complicated, right? Now, when the number of crimes that you see in any urban environment is typically large, and there are lot to say about that from a sociological viewpoint, but we're not going to go into that. Here's an example of what it looks like if you take any 2 weeks. This was in 2017, but you take any 2 weeks, it pretty much would look very similar. Property crimes, 2 weeks in summer, I think it was April 1st to April 15th, and violent crimes kind of seem to fill up the space. And it's not just Chicago. I'm not picking on Chicago. If you go on and look at any other city, any other sufficiently large urban space, you will see pretty much the same thing. So what I was saying that earlier, that crime doesn't diffuse out from particular hotspots, because that's not the topology of the environment. You have roads, you have bus routes, you have neighborhoods spaced out in certain ways, and then you have areas where there's no one there, so no crime happens there because there are no perpetrators or potential victims. So there is this urban topology that wires this space, and you have to take that into account, or any predictive algorithm that you are trying to design has to take that into account, and it just can't assume things are diffusing out like a blot of ink, right? So how would we do that? I mean, to be really complicated to incorporate all that information and then try to figure out predictions, right? So the thing about having a large amount of data on events that we can now have is you can ask something like an AI to automatically back out all those patterns and all those relationships without kind of telling it where those relationships should be, right? So data kind of gives us a way to solve those problems. Now, we are not going to get into too deep into how exactly the algorithms work, but we can still think about a little bit about what is the underlying intuition here, right? So the underlying intuition is you discover patterns, discover predictive patterns, maximally figure out all possible predictive patterns that you can distill out from the data that you have, and then you use all those patterns to make predictions about the future. It almost seems like an obvious thing. And in some cases, or in some sense, it is pretty obvious, right? So, for example, when you see dark clouds in the sky, you infer most of the time correctly. If the clouds are really dark, then it might rain, and you'd be correct in that assumption or that prediction most of the times. And the reason why that works out is because, or the reason why you make that prediction is because you have seen that happen in the past. You have seen that when there are very dark clouds in the sky, then it rains or there's a storm afterwards, right? So it's pretty similar to what we are doing here, except the patterns are not as simple as this. They're more subtle, more complicated. The relationships might not be as deterministic as this, and you have to have sophisticated statistical learning algorithms to get those patterns out, right? And also, it will not be one single pattern. The patterns kind of interact with each other, and constrain each other, inform each other in complex ways, in such level of complexity that it might be even difficult to explain that why a particular prediction is arising. There are some things we can do. They can, to some level, we can go or push that idea of explaining why something happens. But really, the patterns that an AI algorithm comes up with are best used by a machine, and that might not be, there might be issues of making them completely human interpretable. So, okay, so we have all this data about past events, and maybe if you can dig into that, you can come up with predictive structures that allow you to predict the future. So basically, we can go and maybe try to make an algorithm that predicts future crime. Now, what properties should such an algorithm need to have to be acceptable for use in law enforcement, right? That's a very important question, and something that we have learned from past efforts, like past attempts at coming up with this sort of thing. For example, your predictions cannot be self-fulfilling prophecies. If you are, what I mean by that is, if you are predicting that this particular region, a particular location of your urban environment that you're interested in, your city, say Chicago, is going to have more jaywalkers, and you send more police officers to monitor that area to find more jaywalkers, that is, people not obeying the walk signal, then you will find more people who are walking when the signal is still green. So that is kind of an example of a self-fulfilling prophecy. You looked harder, so you found more crime. And if that's your metric of whether your algorithm is working or not, and if you are really happy, see, my algorithm predicted there'll be more crime, there'll be crime in this area, and I went looking and I found some crime, trivial kind of really crime that you can uncover if you look harder, then that's not really good. What you need to kind of validate these tools with is whether they can predict crimes which do not show up because you looked harder. Severe crimes, homicides, assaults, stuff like that. I'm assuming rather, that at least in American cities, if you look harder, you will not find more homicides. So that is kind of important. It's also important to restrict applicability of these tools to crimes which are not citizen reported, because different communities have justifiably often different levels of trust in law enforcement. So in some parts of a city might not, the reported crime rate of certain crimes might be lower because they are just not been reported. But again, if you are restricting yourself to the really severe crimes, then maybe that objection can be addressed somewhat. And then there's a notion of then there's the issue of transparency, right? It's not just enough for your algorithm to be fair; it also has to have the it also has to look fair, right? So if you're having like secret lists and stuff like that, that is at the back of the design process, then that's not going to work. That is going to not be not be welcomed very well by the communities. So, and more importantly, we have to kind of somehow at least begin to explore the interaction between crime, social factors, enforcement, because all of that really, you cannot really decouple it. And so those are the features or the properties that absolutely have to be there. And you also need to probably have, it would be great to have a tool which predicts crime, but also can investigate or analyze the different patterns of enforcement and reveal if there are existing biases in that. So that would be a good thing to have as well. Okay, so let's try predict crime in Chicago. So what we do is we break up the city into this spatial grid, and in each grid we see at what time points different events are happening. So essentially, at each of those grid tiles, you have a time series. That's what we call it, sequence of events in time. And we find out what are the dependencies, the cross dependencies between different grid tiles. So if there's some crime happening in A, does that make it more likely to happen in B or not? And these relationships come out not as simple as what I just described. It kind of comes out in subtle and non-trivial ways. The key point is, in whatever I'm talking about, the approach that I'm describing, there is no manual selection of factors, right? So we are not saying that this part of the city has more crime, this has less crime, or go look for certain people. That is definitely not what's going on. No creation of lists. There's no lists being generated of individuals. And we are only using de-identified data. So it's kind of important to mention here this notion of what it actually is predicting, or what we are trying to predict here. We are trying to predict these events in space and time. What happens when it happens? That is what we are aiming to predict, not if certain individuals are going to commit the crime. So even if this algorithm that I'm talking about, describing, gets everything right, all it will predict is there will be an event of this type at this time at this place, and it has no idea of who is going to be the perpetrator or who is going to be the victim. So the data that we train on, that we start on, that we kind of input to the system is precisely that, an event log. What happened, when it happened, and where it happened. So latitude, longitude, timestamp, and nature of crime. And we kind of have that data from the city of Chicago, who puts it out publicly at a 7-day delay. And we have data going back to 2020, about 20 years, 2001. But we only use data going back about 3 or 4 years. So now you have this about 3,000 grid tiles laid on the city that leads to about, and there are 3 kinds of variables: arrests, violent crimes, non-violent crimes, or property crimes. And that results in about 9,000 variables. If you think about pairwise interactions, that's about 40 million binary interactions that you can learn, and about 1 billion or more possible models that you can extract from it. And then the predictor, the kind of the assembled predictor, brings all of this together, and with that, it can make future predictions. So really, the prediction problem, as I said, is predicting events, in this case, criminal infractions, sufficiently ahead of time. In case of Chicago, we're trying to do a week in advance and make the predictions precise enough. So in both time and space. So in space is within a couple of city blocks, and in time is ±1 day. And again, we are using only data that is realistically and cheaply available, and de-identified data, which is really the event logs. So let's take a look at how that looks like. This is not a simulation. This is actual data. And you can see what the time ticking here. So the red dots are actual events, and the cloud is the risk cloud that is predicted about a week in advance, right? And this is violent crimes. This is like all crimes, and this is arrests made during that time. So you can predict in the Chicago data set, we have data on the arrests as well, so you can predict that dynamics, which is very, very coupled to the crime that's happening. Not exactly coupled, but related. And okay, so how does the performance looks like in numbers? We have about 93% accuracy, 87% AUC, 70% specificity at 80% sensitivity. What that boils down to, that if there are 10 actual crimes, then the algorithm predicts 11, out of which 8 are correct, 2 are missed, and there are 3 false alarms. So very, very actionable. And all of that is going on. The predictions are made a week in advance, and the crimes are happening within a couple of city blocks. So you can use this to, well, I don't know, come up with better enforcement policies. What it does not kind of tell the policy is to flood areas with police officers. That is not going to help, and that is also not what the predictions actually are trying to say. It tells you that you can make it much more precise. And let's look at some other places. And we did this with about 8 cities in the paper that was linked to at the beginning. But since then, we have expanded it and looked at data from a few other places, both inside in US and abroad. And let's share a couple of few of those results with you. So this is Boston, the area with data between January 1st, 2021, and July 22 of 2022. And again, as I said, if you plot any sizable urban space, the distribution of events looks kind of scary. Like these are that many crimes that are happening. I think this is about a week again. So a lot of crimes, a lot of events. That's expected. And you can see the distribution of different crimes. Boston has a much lower crime rate than Chicago. So really the top event is something like larceny. But then you also have aggravated assault and other kinds of events which possibly are of greater concern. So what kind of results do we get, predictive results do we get in Boston? So here the training period, and this data is not public actually. So in this training period was in January 1 to March 31st, 2022. It's about 1 year, 3 months. And we did the out of sample test from April to July. So that's like April, May, June, July, about 4 months. And the spatial tiles here were equally small. I don't know whether I mentioned how big. Yeah, I did, a couple of city blocks. So in this case, it's about 0.2 miles across, which is about 100 yards width, 300 yards breadth. And we looked at club the events together as property crimes and violent crimes. And you get pretty similar performance. You get a property crime AUC of 81%, violent crime 84%. And again, it pretty much almost reflects exactly, if you kind of round up the numbers, what Chicago performance was. 10 crimes are committed, it raises 11 flags, 8 correct, 3 false positives, and 2 false negatives. That's pretty good. And again, in this case, we are predicting a week in advance. Now, this parameters are how far ahead in time you can predict and how well the predictability is going to come out to be is a function of the data. It's a function of the place you're looking at. It is not a constant thing. So for example, in Philadelphia, it turns out that we can effectively predict only up to 3 days in future, not a week in future. And here are the results of that. So training we did in Philadelphia was from January 1st, 2016 to December 31st, 2018. And the out of sample test was 4 months after that. But here we are trying to predict 3 days in advance and not a week in advance because the predictability kind of drops off after 3 days in Philadelphia. And the spatial tiles are pretty much the same size, so a couple of city blocks there as well. And here, the performance is something like this. If you have 100 crimes, you raise about 103 flags, out of which 90 are correct flags, 13 false positives, and 10 are missed. So if you bring it down, the reason why it is stated in terms of 100 crimes is it becomes very close to 1. The numbers are very close. So if you are thinking in terms of what happens if you bring it down to a level of 10 crimes been committed, then it raises on average about 10 flags, out of which 9 are correct, about 1 false positive, and 1 is missed. So again, very, very actionable. In fact, when we have this analysis in the paper, but once the paper came out, someone from the Philly Inquirer reached out to me and asked me if we could give a specific example. In fact, he cited one event. Could you have predicted this event? So before we go into that, show you that. So this is what the Philadelphia prediction looks like. In this case, the triangles are actual events. Blue triangles are violent crimes, red triangles are property crimes or non-violent crimes. And the clouds, blue and red, are the predictions made 3 days in advance, right? So the thing to look at, to kind of take away from this animation, it's not really animation, it's actual data overlaid on the predictions, is to see how well the clouds track the actual events, which are the triangles, right? And so as I was saying, this journalist from the Philly Inquirer reached out to me and asked me if we could predict this particular event, which seems to fall within our prediction window, out of sample prediction window, conveniently. And could we have predicted that? So that was a double homicide that happened, that kind of went down on January 7th night, January 8th morning, 2019. And the question is, could we have predicted this? And the answer, when we looked at the data, is yes. This is the prediction for January 7th or January 8th morning, 2019, made 3 days prior to that. And I've overlaid the actual two events, which in this case are the double homicide that I'm talking about. And you can see there is an elevation of a violent crime risk around that area. So you could have predicted this. You could have predicted this. And this was a kind of a crime that happened in a gas station. So there are multiple ways, or we could have interfered or intervened in multiple ways where hopefully the idea is that you could have averted the crime, so there would have been no victims and no perpetrators. Okay, so I'm not going to go into the underlying math that much. If you have questions on that, I can talk about it. But really, one point that needs to be made is the AI that we are using here is not like a neural network. It's not a neural net, right? And in certain circles, that would be a much more controversial comment than the fact that we're predicting crime. And we tested this. We took our data and tried to model it with many different flavors of off-the-shelf machine learning models, and they didn't work out that well. And one of the reasons why they don't work out that well, that we think, is the level of stochasticity that is there in this kind of phenomena, this kind of system. It's kind of hard to learn with the amount of data that we have. So we actually had to build up a framework that is designed bottom up to learn stochastic phenomena like this, or rare extreme events in complex systems. So that's what it does. We call that a fractal net. And it's not just tuned to only learn about crime in urban scenarios, but actually is designed to learn systems like this, events happening in complex systems where there are tens of thousands of different variables that are interacting, and you're interested in predicting or understanding how certain events transpire. So the crime in urban spaces is an example of that. The other point that needs to be, we need to kind of understand about this, that it's not just a predictor. What we are actually finding is a model that connects crime, enforcement, and essentially social interactions. It's a model of social interactions in the urban environment. Really, in this case, we have applied it to crime, but even then, it is really not just making point predictions. It is really a much more complex generative model. So we like to call it, kind of attach to it the idea of a digital twin, if you may. So you have your actual system, if you have your real physical city, and if you have enough data, you can learn a really complex model, which you might not be able to just understand why certain predictions are happening the way they are. But what you have now is a computational model of this really complex interactions that are transpiring between crime, enforcement, social factors, and so on, right? So what does that help us do? That helps us to go beyond just predicting crime or making this yet another predictive policing effort, and do experiments on our model. So we can say, since our model is this digital twin, which is generative, we can say what happens if the crime rate goes up in some places or goes down in some other places, right? How does the future or immediate future change? Or what happens if I change my enforcement policy by looking for more crime in some places or taking away resources from some other places? What happens then? How does that change this, again, immediate future? How does the dynamics continue to evolve? And we found something. We did this kind of push and pulls in our models, and we found something very interesting. We found that there's a clear signature of enforcement inequity. So what we found, to be specific, is when you look at regions or parts of the city which are more well off, the crime rate kind of tracks the arrest rate. So crime goes up by 10%, arrests go up by roughly 10%. But at the same time, what happens in the places which are not well off, poorer neighborhoods, the arrest rate actually crashes. So it kind of seems like if crime goes up in more well-off neighborhoods, it kind of sucks in resources from surrounding not so well-off neighborhoods, so that those latter areas are not kind of ignored, so to speak. And once we saw this pattern, we actually looked into different cities. Every city we looked at, we kind of had the same pattern, that when you change in crime, and this is kind of a nice metric to look at that in this one, the deviation in the mean percentage change in arrest rate per unit change in crime kind of goes in opposite directions depending on whether they're looking at a high income neighborhood or a much poorer neighborhood. So that is kind of very interesting. It's not obvious to that this factor exists, this kind of effect exists by looking at the data. By doing this kind of analysis with this kind of generative model, it kind of teases out these different biases. So that's kind of one real advantage of coming up with this kind of digital twin of social interactions. So what we have right now, and this would be pretty much my last slide. So you have this ability to go from large amounts of data using AI to finding this kind of digital twins, not just making point predictions, but really coming up with a detailed, high fidelity computational model of this really complex systems of interest. So that allows you to do precise predictions, yes, and that is these precise predictions that kind of give us confidence that our model works. But really, you can then turn it around and also predict and discover and quantify biases that might exist. And also, you can use this, and we are hoping as authors that's kind of becomes the dominant use of this technology. You can actually use this to validate policies before implementing them. Right now, if you think that maybe my enforcement policy should be like this, maybe I should spend more money in this kind of social efforts, but it would be much better if you could actually formulate the policy and see what would actually happen in the real system before enacting it, right? So this kind of ideas we can do like this, with tools like this. And I will round off with a couple of comments. One is, so AI, if you're feeling nervous about AI, well, AI is here to stay. That's not really is not really optional whether AI would continue to develop or not. It's going to. So really the question is what we do about it, right? Or how that integration of our society and our values with AI and AI-enabled technologies occur, right? So AI, any kind of predictive technology, empowers a state to do more surveillance, to essentially take away individual freedoms and all that. The only option left is really to come up with tools like the one that I just described, where the data is open, the algorithm is open source, so anyone can actually run this if they have a sufficiently powerful machine, which means that you can turn the tables and make this something that also audits the state, right? So democratization of AI, that's the other point. And the last comment I'm going to make, I promise that I'm going to come back to the issue of free will. If it bothers you that a machine can predict whether someone would get up in the morning and go commit a homicide, then think about this. Is it more unsettling that those actions, going and murdering someone, is somewhat predictable and is somewhat can be attributed to circumstances which make it predictable? Or is it like completely random, that people will wake up randomly in the morning and decide to go and commit a crime like that? So which one is actually more, makes you more unsettled? So I will leave you with that, and we can take questions.
Well, thank you so much, Ishanu. As you said, we'll go ahead and move to questions. I will apologize in advance. We have a ton of questions, so I know that we won't get to them all, but we're going to dive in. To start, we have a few questions just about the measurement, room for error, and all of that. So can you talk a little bit about how you deal with measurement error, particularly recognizing that you're using data that's generated by the police? And so there's some questions about how you can be sure we're not encoding bias from the police in the data to begin with.
We are absolutely encoding bias. There's no doubt or question about that at all. And it's not that anyone is sitting down and kind of creating fake kind of events. That's not happening, because all the events are have an ID which you can actually check against a national database. So that's not it. But the fact that you're finding more crime because you're going and looking for it, that effect is always there, and you can't really decouple it. So all the data that we're looking at is reported crime, as you quite aptly said. It's not the crime what is happening, but what is reported. And there's really no way of decoupling that, at least not that what I can think of at the moment. Our kind of approach to handling that was to focus only on severe crimes. So we didn't look at drug crimes at all. We only looked at violent crimes and severe property crimes, right? So that kind of addresses that. As I said, I'm hoping that that if police officers go look for more homicides, they're not finding more homicides. I'm hoping that is true in US. So.
And with the AI, is there a way to figure out the reason for the predictions? Like, can you see what the model is prioritizing or discounting, particularly if it seems like it's a rare occurrence?
Yes, you can, but it would not be something that you can after the fact, right? You cannot do it before the fact. So you cannot learn certain patterns and run it in your head and make predictions. So the models are really complicated. So as I said, there's about 1 billion possible sub-models that can exist. Not all of them are active all the time, but it's really complex. So the way to think about it is, I mean, there are a lot of work going on explainability, and that's a really hot topic, really open topic. AI systems are typically and notoriously hard to explain. And if you ask me how I feel about it, I think the fact that you can't explain those things, that some of those systems, is because they are complex systems. You can't say that here's trying to predict tornadoes, for example, another complex system, like rare and extreme weather phenomena, right? You cannot say that there was this really complex system that we have, and it produces this sometimes, from time to time, these tornadoes, and then I apply AI to it, and it becomes like a 2-variable something that I can write at the back of my hand. That's not going to happen. It's something like a conservation of complexity thing going on there. So the model would still be complex, but then if your model is really good and predictive, then you have a digital twin kind of thing, which means you can tug and pull up on it. You can basically do things which you cannot do on the real system, right? So for example, we can say that what happens if crime goes up in this part of the city? You cannot do that experiment in real life. Ethics apart, I don't know how you do bring up crime in a particular part of the city. So you can't do those things, but in this case you can, right?
And do you see any difference, or what difference do you see between what the AI is predicting and what we would maybe expect if we looked at seasonally adjusted averages or something along those lines? Yeah,
you won't be able to, your AUC would pretty much be terrible, would be like close to 50%. So seasonally adjusted averages only work for the entire city, right? In large places, right? So it would be, the predictions would be trivial. If you were saying like, there will be a crime tomorrow in Chicago. Yes, you were correct 100% of the time, also completely useless, right? So it's like predicting earthquakes. If you say that there'll be an earthquake tomorrow somewhere, then that is true actually, but also not very useful. Yeah. So that space and time boundary is what makes it useful. You have to predict it sufficiently ahead in future, and you have to bound it both in space and time, right? So earthquake example, if you say that there'll be an earthquake somewhere on the planet, that's not very useful. If you say there'll be an earthquake in California in the next 10 years, again, not very useful. So you have to kind of bound the space-time, and then it becomes useful and actionable.
Well, and that I think leads to another question that we have a couple of versions of, which is really how and when is this data being used to have meaningful impacts on safety in large cities? Are you sharing it with law enforcement, with policymakers? Sort of how is this data being used now?
So yeah, we are not. So when we wrote this paper, we had actually thought long and hard about this, because we don't want it to be like a repeat of the broken window policy thing, if you're aware of that. So sometimes if an author of a paper and gets published, you kind of lose control over it, or the narrative to some extent. So we didn't want that to happen. And we also didn't want it to just become a predictive policing tool. And if you read the paper, right in the title, we kind of emphasize that the idea of this is to see, we have a tool, it is good because it makes good predictions, But really, the application of this is to optimize policy. So we are having some discussions with some groups, including the Council for Social Innovation in Illinois and some other places. There have also some interest from law enforcement, but since we have really not made any effort to commercialize this or anything like that, so we have not progressed too much, or we don't want to do that, basically. So, but then one of the good things that we thought would be great was to have the code, the software in the public domain. It's not in the public domain. Let me take that back. It is not in the public domain, but it is accessible completely. So, and the data is public, so anyone can actually use it, and they can read the paper which describes how to implement it. So if a law enforcement agencies implement it themselves, then well, they don't have to ask me to do that. So.
And I mean, this may be getting kind of beyond how you kind of see the paper being used, but what do you imagine that police or policymakers could do to change some of their enforcement strategies using the data?
So, as I said, we are having some conversations with police departments, and mostly my kind of sense of it is there has been a reduction in number of personnel that people have, these departments, this captains or commanders have at their disposal, and they are really looking for ways where they can do their jobs more efficiently. They don't really want to, yeah, so that's kind of it, that they really want to do their jobs more efficiently. And if you have this kind of predictions working, or this kind of predictive tools in play, then that reduces how many personnel you need to do the same thing. So it reduces costs, and that should make everyone happy. So I think that would be a good thing to do. But I would really like to see this where it kind of impacts and changes policy.
And we have a few questions about how else you might see the model being used. So for example, would the methodology be transferable to predicting other causes of death, like suicide?
Not the particular tool that we're talking about here, right? The particular tool that we are talking about here is one that learns from the spatiotemporal phenomena and tries to predict how the dynamics would play out in future. So suicides can be predicted, well, some part of it, depending again on what do you mean by predictability? Like suicidality rates are pretty stable, but if you are talking about whether individual is at risk of suicide, there are some work that is coming out where you can think about that, but that has nothing to do with the spatiotemporal aspect of it, right? So that's not like a rare and extreme event in a complex system.
Yeah. And we have a couple of people who've asked if you can say a bit about the variables or predictors that you found to be most strongly correlated as kind of predictors of crime, and if there are any that surprised you.
So, and this is probably, I should have spent a little bit more time describing what the inputs are. I did talk about it very briefly, touched on it. So that's not how this kind of approach works, right? That is really a slippery slope. If you start putting out that here are the factors that drive crime, which means you need someone sitting down somewhere and making that list, right? Maybe you come up with a really large list and you say that, oh, well, it's not biased because I included almost everything. And then the system picked out some of it. Well, it's still biased because you didn't include everything. You just thought you included everything, you didn't. So anytime when you're coming up with those features, a list of features, then there is that risk of injecting bias in the system, even if you are not intentionally doing it, right? So how this approach works is the only input data is the event log and nothing else. There are no factors that we're considering separately. There are no features that I'm identifying or a list of features or potential features that might inform the system. It's only based on the event log, right? So it's kind of completely hands-off. You can really connect it to the data portal that Chicago puts out, the data every day with a delay of 7 days. So every day it updates it. You can connect it with that and it can run on its own.
Okay, very interesting. And so we have a couple of questions too then about like just in terms of actionability. If you can tell, for example, if police officers were allocating more police based on the model, do you see the predicted crime rates go up and down if some of those variables change?
So that's an interesting question. So we have not deployed it prospectively. So that's one thing. But what we do see is if you change law enforcement effort, how that affects the crime rates depends on where it is happening. That's one. And yeah, okay. So that's pretty much what we see. That it's a function of where you are doing this, because and that's one of the ways we kind of probe for bias, because there are some things where conditioned on crime, the enforcement should be independent. The number of arrests should be independent of where you are, right? Conditioned on crime. If you're given that this amount of crime has happened, then number of arrests should be statistically independent of where you are. But you see that that is not what we see. So it was actually quite interesting and non-trivial when we started working on this, and we were funded by Neubauer Collegium, and the director at that time was less interested. He's a philosopher and not in CS, computer science or machine learning. And his interest was quantifying bias. He was less interested in whether you can predict crime. He was more interested in whether you can quantify bias. And it's actually quite non-trivial to figure out what is the metric by which we're going to measure bias, right? And we ultimately came up with this, that if you're looking at enforcement decisions, arrests, for example, that should be independent of where you are or what your social background is or whatever, like the SES variables, if you condition on the amount of crime that's happening. And if that is not independent, those things that have dependency, then that's an indication of bias. Which means that the police officers are arresting people not because of crime or something else, which is clearly not what should be happening.
Yeah, which is actually it was the question I was going to ask next, which is that, I think we've talked about a lot of bias maybe working in one direction, but we actually had a question about whether you see space in some of this work to alleviate racial stereotyping when we look at crime and police work.
Yeah, if people I don't know. I mean, just writing a paper doesn't do it, right? It has to be implemented. It has to be taken seriously by the right people, the people who are in the policy-making places. And then it doesn't have to be this algorithm. I think what this work shows that this is possible. So we shouldn't, policymakers shouldn't just come up with policies based on what they feel in their gut. There can be and should be much more detailed validation of that the policies actually do what they think that they do. Right.
So we're going to take a step kind of deep into some of the more technical pieces. And someone has asked, if possible, could you explain the key difference between a neural network and a fractal network?
So yeah, I mean, I can go on for hours on that, but just to kind of summarize at a very high level. So if you are familiar with neural networks, you know that there are things called activation functions, which are not learned. Those are constant functions, and you kind of assemble it, and then you find the weights by which they're assembled, and that's how a neural network kind of is trained. So what a fractal net does is learns those local activation functions, right? So it is no longer like a ReLU function or whatever, some sigmoid function. It's not that. It's something much more complicated, which reflects the local kind of how locally the different signals that you're getting, how it is driving the phenomena. You actually learn that as an activation rather than assuming that. That's one difference. The other difference is that neural networks, if you go and look back at the theory of it, they are universal approximators of functions, not stochastic phenomena, right? So stochasticity and noise are kind of add-ons to it. So there are limitations to what kind of stochastic processes it can actually learn. Whereas fractal nets are designed bottom up to learn stochastic phenomena, particularly when there are thousands and thousands of variables, stochastic processes which are interacting in non-trivial ways that we cannot a priori understand. then that's where it kind of makes a difference.
We have a couple of more questions kind of about the inputs themselves. So wondering if you could talk a little bit about what is collected in the event log, and if I think you said already that there was an additional information, but if there's any other data or information that's taken into account by the tool.
No, it's just event log. It's like what happened, where it happened, when it happened. That's it.
Very straightforward.
I mean, we could have added weather. One of the things we could have very easily added was weather, right? But we tried to make the exposition as clean as possible, right? I mean, we know that when when the weather cools down, becomes too cold, the crime goes down. You clearly know that. Or that there's a temporal periodicity, like crime goes up on weekends and goes down during the week and stuff like that. But in fact, we can see that in the predictions, those characters are actually recreated. The system learned that by itself without us telling it so.
And someone is wondering if you know kind of what the AI said we should expect about crime in 2020 before we knew about the pandemic, if that makes sense. So what would AI have told us in 2019 we should expect in 2020 versus what did we actually see in 2020?
That's a very interesting question. So the paper came out in 2022. Most of the analysis was completed before the pandemic. And well, I was going to say that we applied the tool to data that people reached out to me with, and it still worked well. For example, the Boston data, and there's some other places we looked at. But really, we retrained it. We retrained it with data that was generated during the pandemic as well. So that would be an interesting question. I don't know. If we look at the Chicago models that were generated before the pandemic, if we apply it during or after the pandemic, what happens to the predictability? That would be a good paper to write, actually. I don't know.
So I'm gonna.
But I would say this. I would add this, that since technically my office is in the hospital, and so I'm aware of the rates of the different. For example, the number of people showing up to the emergency, right? And also I can look at the data for that. So crime didn't quite change. The crime rates didn't quite change. At least the number of people who are showing up to the emergency with gunshots, that did not change during the pandemic. Everything else, every other category of people who are being seen in the emergency went down, including kids who generally show up with, I don't know, tummy aches and stuff like that. All of that went down. The only category that didn't go down, not the only one. One of the categories that didn't go down is number of gunshot victims, which was kind of interesting. Didn't go up or go down. We might say that people are staying at home, they're getting upset, and that's why gunshot victims number of them goes up. Or the people are not going out and they're less perpetrators. So none of that. It pretty much remains stable. So I don't know. That can be an interesting thing to study.
So along those lines, one final question for you, which is where do you take this research from here? What are you doing next with it?
So trying to convince people that it's a really not good tool, really interesting and effective tool for policy design. That's one thing. And we also want to look at like global events, not just crime, but if you look at a larger scale, and not crime, like terrorism or things like that, or unrests, like what do we get? There's actually nice databases that are coming up, which record those events and curate that, and has been doing that for some time. So it'll be very nice to see whether we can come up with this kind of predictions at the global scale.
Well, thank you so much. I want to thank you, Ishanu, for an amazing evening. I want to thank all of you for your questions. We had more than 50. So if we didn't get to yours, that's why. But it was a pleasure to spend some time exploring the life of the mind with all of you this evening. I hope you'll continue to engage with the university and with the alumni community, whether that's by attending another event, volunteering, providing philanthropic support for our faculty and students, or simply spreading the word about the groundbreaking work happening at the university. You can learn more about opportunities to do all of these things and more on the Alumni and Friends website. The link is now in chat. But most importantly, I want to thank you all for coming together tonight to celebrate the University of Chicago community. Enjoy the rest of your week.